Hello, I'm Tim Lichtenberg from Oxford. This research project is in collaboration with Joanna Drążkowska, Maria Schönbächler, Gregor Gollerbeck, and Tom Hans. Our project is related to how to build up structure and disks and the resulting consequences for the formation of planets. Now, the relation to the workshop theme is via the abundance of short-lived radionuclides in the solar accretion disk, which must have been due to the presence of an O-star in the star-forming birth environment of the young sun. Now, to motivate the project, we see the familiar ALMA images of substructure in the dust component of disks, and we have complementary evidence from the solar accretion disks in the form of meteorites showing clustering in isotope space in the non-carbonaceous reservoir, which represents inner solar system material, versus the carbonaceous reservoir, which represents outer solar system material. Now, what we do is we try to explain those simulations using a model of the solar accretion disk and the coagulation of dust grains and their drift, the buildup of planetesimal families. This makes use of simulations that were already published by Joanna Drążkowska in 2018 and Drążkowska and Dillmont. This here showing a video. If you want to have more information about the underlying mechanisms of the simulations, please talk to Joanna directly. She will be available during the workshop. Now, what you particularly see is the drift of the snowline from the infall to the disk stage, the buildup of distinct planetesimal reservoirs during the time window, first because of the cold finger effect, and then because of the traffic jam effect. The importance here is that these are two distinct reservoirs which differ not only in orbital distance but also in formation time, which is important for the availability of aluminum-26 heating and the energetics of that process. That is relevant for the formation of iron cores and planetesimals, and therefore meteorite parent bodies, and the availability of water that is accreted from the surrounding planetesimal, from the surrounding accretion disk. We try to match, or we try to explain the meteoritic chronology here, first of the core formation process and hydrothermal activity that is observed in present-day meteorites. Now, our simulations produce peaks of core formation on these planetesimal bursts, one at around 1 megayear for reservoir 1, at around 2 to 3 megayear for reservoir 2. This explains the clustering of ages in the meteoritic record for the NC reservoir and for the CC reservoir. With regards to hydrothermal activity, meaning water-rock reactions, reservoir 2 produces a peak at 4 to 6 megayears, which will produce the clustering of ages in the CC reservoir. In addition to this compositional information, the model suggests an explanation for the isotope dichotomy. If you look at 2 and 15 AU, which are roughly representative of the pebble flux in the inner and outer solar system, you see that the pebble flux over time deviates, which is because pebbles from the outer solar system are built in preferentially into materials in reservoir 2 and make up the outer solar system, therefore leading to a deviation in the pebble flux, and hence, if there was an underlying isotope dichotomy or inhomogeneity of the isotopes, then these would have been preferentially incorporated into the outer solar system. Now, here's a summary of our model, both in isotope evolution and growth chronology, which I'm very happy to discuss with you if you have questions about this. Major points of this are that our model suggests a heterogeneous mode of accretion, from starting with collisions, going over to pebbles, and then transitioning again to late stage phase of collisions. The compositional dichotomy of a dry inner and wet outer solar system is the result, in this case, of a spatially and temporally distinct buildup of planetesimal reservoirs in the accretion disks because of the movement of the snowline, which drives divergent evolution of the planetesimal families and therefore changes the compositional reprocessing in the inner versus the outer solar system, suggesting a different water or volatile accretion sequence than is typically suggested. Additionally, in this model, meteorites are unrepresentative of primordial building materials, and leftover planetesimals like meteoritic parent bodies should form with layered structures of inhomogeneous composition. Thank you very much for your attention.